First, let's look at the physical properties. These include appearance, color, odor, boiling point, solubility, and polarity, among others. These properties depend on the attractive forces working on the molecules. As we have learned, alkanes consist of only carbon-to-carbon and carbon-to-hydrogen single bonds. These bonds are covalent, and the electronegativity between two carbon atoms or between carbon and hydrogen is almost negligible. Hence, the molecules formed are non-polar. This is why the only attractive force acting on these molecules is the weak van der Waals forces. Therefore, the first four members of the series, C1 to C4, are gases. C5 to C17 are liquids, while the molecules containing 18 or more than 18 carbon atoms are solids at 25 degrees Celsius. They are all colorless and odorless. Due to their non-polar nature, these compounds are insoluble in polar solvents like water and soluble in non-polar solvents like benzene. Their boiling point is decided by the strength of the van der Waals force. This force is very sensitive to distance. Hence, for a strong force of attraction, the molecules need to be held close together. However, in alkanes, because of their non-polar molecules, the van der Waals forces are weak, and hence their boiling points are much lower than expected. As the size of a molecule increases, its surface area increases. Thus, the strength of the intermolecular van der Waals force also increases. A linear or straight chain alkanes like pentane has a higher boiling point than its branched isomers like 2-methylbutane and 2,2-dimethylpropane. This is because branching reduces the surface area of a molecule, leading to a weakening of the van der Waals forces, which are then overcome at relatively lower temperatures. Now, let's look at the chemical properties of alkanes. As we have seen, alkanes are non-polar. Their carbon bonds are quite stable, and so they do not easily react with acids and bases. However, they do undergo substitution reactions and combustion reactions under certain conditions, as their carbon atoms are in strongly reduced states. During this reaction, the hydrogen atom of an alkane is substituted, and hence the reactions are called substitution reactions. When the element substituting the hydrogen is a halogen, the reaction is called halogenation. It involves 3 steps: initiation, propagation, and termination. Let's go through each step by observing the chlorination of methane. During chlorination of methane, the 4 hydrogen atoms of methane are step by step substituted or replaced by chlorine atoms, forming tetrachloromethane as the final product. During initiation, the chlorine molecule is homolyzed in the presence of heat or light, forming chlorine-free radicals. During propagation, 2 reactions take place. First, the chlorine-free radical attacks the methane molecule, forming a methyl-free radical and hydrogen chloride. Next, the methyl-free radical attacks the second chlorine molecule, forming chloromethane, and 1 more chlorine-free radical, setting up the chain reaction. The chlorine free radical formed sets up many other propagation steps to form more halogenated products. These steps are repeated till all the hydrogen atoms in the methane molecule are replaced by chlorine atoms. During termination, the reaction stops either because all the reactants have been consumed or because of the following possible chain terminating reactions. One possible reaction is that two chlorine-free radicals combine to form a chlorine molecule. Another possible reaction is that two methyl-free radicals combine to form ethane. Or a chlorine-free radical and a methyl-free radical combine to form chloromethane. Thus, in the chlorination of methane, ethane is obtained as a byproduct. Now let's understand the combustion reaction of alkanes. On heating, alkanes get completely oxidized to carbon dioxide and water along with heat. In the presence of air or dioxygen. This is why alkanes are used as fuels. When alkanes undergo incomplete combustion, they form carbon black. It is used in the manufacturing of ink, printer ink, black pigments, and as filters. Alkanes, like methane, on heating at high pressure with a regulated supply of oxygen and in the presence of a suitable catalyst, provides a variety of products like methanol and methanal. Ethane gives ethanoic acid. And an alkane with tertiary hydrogen atom like 2-methylpropane gives corresponding alcohol. When a normal alkane like N-hexane is heated in the presence of anhydrous aluminium chloride and hydrogen chloride gas, it isomerizes to a branched chain alkane like 2-methylpentane and 3-methylpentane. Alkanes undergo aromatization or reforming. That is, a normal alkane with 6 or more than 6 carbon atoms like N-hexane, when heated to 773 Kelvin at 10 to 20 atmospheric pressure in the presence of a catalyst like oxides of vanadium, molybdenum, or chromium supported over alumina, gets dehydrogenated to form cyclic compounds like benzene or its homologues. Alkanes also react with steam. This reaction is used in the industrial preparation of dihydrogen gas. For this, methane is heated at 1000 degrees Celsius in the presence of nickel, along with steam to form carbon monoxide and dihydrogen gas. Higher alkanes at higher temperatures decompose to form lower alkanes and alkenes, amongst others. This reaction is also known as pyrolysis or cracking.